Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me is.
Robert Moore.
So, Robert, this is our 13th episode of season number 2.
Yep.
If anyone out there who is listening live, please feel free to submit your questions or your comments by the live chat that we have running. Today, we have a very special guest, Dr. Bonnie Buratti from NASA's Jet Propulsion Laboratory. Bonnie is a senior research scientist and principal deputy project scientist for the Europa Clipper mission, which is something we'll get into today.
Right.
I'm sure. So, Bonnie, thank you very much for joining us.
Thank you for asking me.
So, to get into it a little bit, I guess we could start with the most exciting thing, and that is the Europa Clipper mission. So, do you want to explain to people what it's all about and what is the sort of the primary objective of the mission itself?
Sure, thank you. So I don't think, there's any question more important than are we alone in the universe? And, when I was going to graduate school, I got my doctorate at Cornell, and, I was Carl Sagan's student. I was working in his lab, and, there's the creation of all this kind of gooey stuff. Tholins is what he called them. And at the time, we thought that life started in the shallow seas of the earth, where there were this warm oceanic water, and it got zapped by lightning and amino acids formed, and by some mysterious process life formed. And this is what Carl and Abhishankari, his collaborator, were showing in their lab. If you took these vials of water and other chemicals and zapped them with electricity, you would get this organic material. Well, now we think that's wrong. The most common opinion on how life arose on the Earth is that it was in the deep oceans. You have these thermal vents, sometimes called smokers, that scientists, biologists have noticed have all this primitive bacteria, these primitive life forms, that material, that life forms that you see at the base of the tree of life from which everything arose. So now we think that is where life formed, in those deep, warm, oceanic vents. So along with that trend in scientific belief, there was this other thing happening in space exploration, that we began to see that all these worlds had oceans, but the oceans were underneath the surface. Life as we know it requires three things: liquid water, that's life as we know it, some form of energy, and also some form of food. So, Mars, scientists tend to look at Mars where there was water, there probably was liquid water in the past, maybe life arose and it kind of hunkered down right below the surface. But then scientists started to see that there were all these objects, many of these objects, moons and planets in the outer solar system, that had liquid oceans underneath ice crusts. So one of the candidates for that particular scenario was Europa. Europa is one of the 4 major moons of Jupiter that was discovered by Galileo in 1610. So when the Galileo spacecraft, there's Galileo the man and then Galileo the spacecraft. When Galileo, the spacecraft, went by Europa, it discovered, based on the fact that there seemed to be a magnetic field induced. In order to have a magnetic field, you need a conductor. It seemed the only thing that could cause this magnetic field was salty water underneath this ice crust that we saw at the surface. So lo and behold, Europa had this ocean underneath. In fact, there's more water on Europa than on the Earth. So scientists, just in the last couple of decades, have started to look earnestly for habitable environments on these ocean worlds. And the Europa Clipper mission is the first detailed look at an ocean world outside the Earth. Now, I should mention that there are 2 things. First of all, we did get a fairly decent view of Enceladus, which is an ocean world around Jupiter. I'm sorry, around Saturn. It's around Saturn. And we actually saw active plumes on that during the Cassini mission. But we didn't send out a specific mission to look at this object. We just discovered that it was an ocean world. And also we didn't get as close a look at Enceladus as we're going to get at Europa. The other point I'd like to make is that we're not looking for life. We just don't have the capability of looking for life itself. What we're looking for is what scientists call a habitable environment. That is a place where life could exist and thrive, evolve. So that's the fundamental goal of the Europa Clipper mission, to search for a habitable environment.
Now, the Europa Clipper mission itself, so if I understand right, it's going to go in orbit around Jupiter in 2030.
Mm-hmm.
So will it have the capability to study some of the other moons of Jupiter besides Europa, or is it 100% focused on Europa?
Well, the prime focus is Europa. We are making some flybys to the other major moons. In fact, we fly by Ganymede, which is the third Galilean moon out. It's Io, Europa, Ganymede, and Callisto. And we will be going by Ganymede, and we'll be looking, but it's just to calibrate our instruments. I mean, we may get some serendipitous scientific observations, but right now we're trying to stay on budget by focusing just on Europa and not planning any observations of any of the other moons. But after we launch, I'm sure this is, scientists, we want to discover and learn as much as possible. So, we'll certainly be asking for that, but right now there aren't any plans.
Yeah, so it's a nominal, 4-year mission? Is that true?
Yeah. But as you know, NASA always has extended missions. I mean, if you spend money to go out there, you might as well make the best use of that money. So yeah, it is right now. It's the nominal mission is 4 years.
As long as you've got power and a working craft, why not? Right?
And it takes a while to get there, because the exciting thing too, I know sometimes we talk about things that are happening and they always seem to be in the distant future, but Europa Clipper is going to be launched this year in October, if I'm not mistaken.
Right.
So
Yes.
that's happening pretty soon then. So there's going to be a lot of media hype about it when we get close to the launch date.
So half a year, 6 months? Yeah.
Well, if I remember right, the original, one of the things they were suggesting, at least when people were at NASA were proposing this mission, I don't know if it was a selling point for the SLS, is to try to put it on the SLS. But as we know, they're not cheap, a single launch, and we've only had one launch.
Okay.
So that, if you probably want to have a few launches, well, the next launch is going to be people on board. So there's no waiting around to look at the reliability of the rocket itself. But if I understand right, it's now going to go on a Falcon Heavy, and that would significantly reduce the cost. Is that true?
Yeah, that's true. The issue is that we did originally want to go on an SLS, but one wasn't available. So we had to go with the Falcon Heavy. And what that does is it does increase our cruise time significantly. And the reason for that is the Falcon Heavy isn't powerful enough to send our spacecraft on a direct trajectory to Jupiter. I mean, it has to escape the gravitational well of the sun, and the energy just wasn't there. So it has to do this thing that JPL has done many times in the past, a gravity assist on the planets in the inner solar system. So about 4.5 months after launch, it's going to go by Mars. And how this works is it flies towards Mars, and it goes into its gravity well and basically picks up speed. It picks up momentum just falling into its gravity well. It goes by Mars, it swings around, and then it goes by Earth, picking up additional velocity, and then out to Jupiter. It's going to take about 5.5 years, almost 6 years to do that.
Wow.
Right, so that's like arrival time in 2030 or something, right?
Yeah, in April 2030,
Yeah,
right.
right.
Okay.
I mean, I remember in the Voyageurs, so in the late 77, Voyager 1 and 2, and they were launched like directly right towards Jupiter. It was an Atlas Centaur vehicle or something, if I remember right. So that had the power to go direct rather than the slingshot,
Right.
the longer approach.
Well, that's one thing people don't realize is I keep getting asked, why didn't we go back to the moon? Well, one of the things is we didn't have a rocket powerful enough after we ran out of Saturns and Atlas, it just wasn't there.
Yeah, that kind of, Bonnie, when you think in the future, if everything works out okay, and not thinking specifically about the SLS, but things like Starship, with Elon Musk, doing these test flights and stuff, that I think that's one of the goals is if that became available in its sort of, prime configuration that they envision, that will really help planetary science in a sense. It should make it a lot cheaper per pound if you like to send, spacecraft to the outer solar system.
Yeah, that's true. And also we're getting better at making light spacecraft and lighter instruments. One of the advantages, the outcomes of the space program is that we've been able to miniaturize electronics and components, and we're continuing to do that. So that's another factor that we can do more with less.
Right. I mean, you can think of, some really fantastic follow-up missions to Europa.
Oh, yeah.
By the way, if you're a science fiction fan, aren't we told not to go to Europa?
Yeah, yes. In fact, I think what you're referring to is the radiation environment. Is that it?
2001
With
Space
2001
Odyssey.
reference there.
Oh, there could be a light. There could be light
Yeah.
there. Yeah, there's that. Yeah, there's the two things there. Yeah.
Yeah, that was the part 2 of 2010 or something.
Yeah, all
was
these
it?
worlds are yours except Europa.
Yeah, stay away from Europa was
Yeah.
the sci-fi.
But
yeah.
yeah,
But you
but the radiation is a problem.
Yeah, well, I was thinking of missions. It's easy to dream about stuff. I don't have to pay for it, right?
Right.
Or put in the time and investment of effort to make it happen. But you can imagine in the future, and hopefully this will happen. Landers landing on the surface of Europa and then having some type of ability to drill down through the ice. Whether it's an internal, like almost like a nuclear power plant to generate the heat to melt their way down, and to explore directly, to sample in situ, if you like, the sub-ocean conditions to see what it's like. And so, I mean, that would be the ultimate sort of mission, if not.
Yeah. Well, here's the issue with that. So, our original payload or our original mission actually did have a lander. We had a Europa lander, but that got descoped because of its expense. But there is a problem. So a lander would be, you'd learn a lot from a lander, although it would be only in one area. I mean, there are other ideas that deploy seismometers and little targeted packages all over the moon. But the problem with the subsurface drilling is we don't really have the technology. Now, if you look on the Earth, we also have, in addition to our ocean, we also have subsurface lakes and oceans. There's is it Vostok?
Yeah, that's right. In Russia.
Yeah, in South America, in Antarctica, and the Russians have actually drilled down there, and the ice crust, of course, is just, I don't even think it's a mile, but it's really, really hard to drill down there. The technology they did manage to do it and found life forms, but the problem with Europa is that the crust, we think it's about maybe 20 kilometers, which would be about 15 miles or so thick, or 13 miles or something, to drill down there, the technology. And it's hard enough to do on Earth where we have these heavy drilling things. To do that on Europa would be exceedingly difficult.
Right.
So, I think it might be more advantageous to have some kind of distributed landers on the surface where you sample at least a variety of geologic terrains.
So what do we expect the terrain to be like? I know we have images from the Cassini mission and the original, Voyager, and if you want to go back even to the Pioneer days, right? The first flyby of Jupiter. What do we expect the surface to be like? What do you envision? And am I thinking like Antarctica, except you got lots of crevices and ridges and mountain ranges and so on, but it's really an ice field? Is that what we should think about?
Yeah. Yeah, if you look at some of the geologic forms, you'll notice that, there's this phenomenon known as rafting, where you have parts of the ice shelf literally, breaking up on either a liquid or a subliquid surface area below it, and it just kind of moves around. There are these ice patches that you can actually put together like a jigsaw puzzle. So there's been the motion of the ice shell cracking and motion similar to that in Antarctica. But there's also another strange thing, in spite of the fact that if you look at some of the Galileo close-ups, it shows a very kind of rough surface, where it has these linea, these areas, these lines that look like something's coming out of them, and a lot of grooves and stuff like that, and these lenticuli that are almost like bubbles coming out of the surface. So we see a lot of those kind of rough features, but if you look at the global appearance, and if you model the surface of Europa with photometric models, it looks like the aggregate surface is pretty smooth. I mean, there's some icy plains that look very smooth, but we think that maybe some of the areas in the moon, the crevasses and the pits are all filled in with the ice particles that may come from activity on the surface. So you might actually have good skiing on Europa. Of course, you have to ski in a spacesuit, and you have to protect yourself from the radiation, but it looks like it might be really good powder out there. So yeah, it's honestly, we don't know, but we will be getting images from the camera on Europa Clipper that will be in some meter type resolution. So we'll be able to see a lot of these features.
So the data from Europa Clipper, will that constrain more the depth of the ocean? Okay.
Absolutely.
Yeah.
There are two instruments that are really going to be appropriate for that type of investigation. The first thing is we have this novel ice penetrating radar. And one of the things, there's a lot of new technology on the spacecraft. The first thing is we have these solar panels that when they extend, they go out as big as a basketball court. They're not the biggest solar panels in space. That honor belongs to the space station. But in deep space, that is non-Earth orbit, they will be the biggest solar panels. They were built by Airbus, and they're down at the Cape. And the reason I bring them up now, because we're talking about, well, how deep is this ocean and how thick is the ice crust, is because this ice penetrating radar, we call it reason, the antennas are actually attached to these solar panels. They're like little antennae, actually too big, and 4 little antennas coming out of the solar panels. This is really a novel type technology. And that instrument, that radar, will be able to probe into the surface. It'll be able to detect any patches of ice and water. In fact, one of the ideas is that there are kind of subsurface puddles of water in the most chaotic, and we actually call it chaotic terrain of Europa. So it's kind of tucked underneath there. But there's another instrument that will be able to measure the global extent of that ocean, and also possibly how deep it is. We think it's maybe about 80 kilometers, 160 miles deep. It's way deeper than the Earth's ocean. That's why it has more water, liquid water, than the Earth does. So this is the gravity experiment, which is just going to use the high gain antenna and the medium gain antenna on the spacecraft. And just by looking at kind of how the moon wobbles in its orbit, if there's an ocean and a crust that kind of wobbles a little bit, it doesn't quite rotate at the same speed, velocity, and then also it'll be able to see how it kind of lags in its orbit. Okay, so that's how we've done similar things on the moon, the so-called librations of the moon. So just by looking at that, we should be able to tell with those two instruments, should be able to tell the thickness of the crust, and if we're really lucky, the depth of the ocean, and whether it's equally deep all around. That's another big factor.
So you could think of an analogy maybe like an egg, where you have an egg that's not boiled and one that's boiled, and you spin them, then you can tell which one is hard boiled and which one isn't, the raw egg.
Yeah, I like that analogy. Yeah.
So, speaking technically, it's the moments of inertia.
Yes.
Yeah, it's measuring moments of inertia. Thank you. Yes.
When you mentioned about the ice penetrating radar, and when you think about radar, I always think about an instrument, at least historically, that's required a huge amount of power. And there I'm thinking, where you're far away from the sun, compared to where we are, that to have enough power to be captured by solar panels, they must be, number one, very efficient, in terms of maybe what we had had several decades ago, and also very large. That's where the wide area would come in. Because normally I would think that, well, let's just put in like a nuclear power type of
An
device,
RTD
right?
or something.
Yeah, radioisotope thermoelectric generators or something like that to power the radar. But in this case, what you're saying is the technology, if I'm not mistaken, has advanced to the point where now solar panels is really able to perform the function that you need for power.
Yeah, yeah. There are a couple of things with nuclear power. I'll start with the kind of the controversial one, which really shouldn't be a controversy, and that is that it's not safe to be putting that material out in space. That could crash back on Earth, but it's perfectly safe. It's completely encapsulated, but there were a lot of protests always when we launched these missions that had nuclear power. But the other reason is that the supply of plutonium was not all that reliable, that missions were almost canceled or weren't able to launch because of that, the nuclear material supply. But going with solar energy was just a lot more reliable. And also, I think it's more sustainable. So now, if you go to the outer solar system, if you went outer solar system like Pluto or the Kuiper Belt, you wouldn't be able to use the sun because, as you know, the energy from the sun goes down as 1/r², so it goes down pretty fast. So
Right.
Yeah.
Right now is the only as far as we can go.
Well, even the Lucy mission, don't they have very large solar panels too, right? And they're not, yeah,
And so does Psyche.
right.
I've got to ask something. You're talking about the radar dish on either end of the solar panels. That means you're also planning on using it as an interferometer?
I think there are some plans to do that. Yes.
Okay.
Yes. Yeah.
Cool.
Exactly. You want to see a picture that if I can share,
Yeah.
is it okay if I share a picture of the spacecraft?
Sure.
Okay. Let's
Yeah.
see. Share screen. Okay, there we go. Okay, so oops. Yeah. So can you see this? Let's see.
Yeah, we can see it.
Yep.
Yeah, okay. Let me just do slideshow because that'll at least you'll be able to see the whole thing there. So there it is, and you can see that. So here are the antenna. Here's the high gain antenna. So it's not going to be using that. It's going to be using these are the high frequency antennas here, and then the very high frequencies antennas are these 4 antennas here. This is really a novel design. This is the first time we've done anything like this.
Wow.
So how far, like in depth wise, can you penetrate down for normal, let's say, ice that you would expect on the surface of Europa?
Yeah, we don't really know. We did use a similar instrument on Marsis on Mars, and that went down tens of kilometers. So we're hoping that we'll go down. Well, it will go down further than that. We're hoping we can get down through the ice.
Wow, it's amazing.
That's amazing. That's
And
incredible.
we'll at least be able to see if there's any water that is in the crust itself. That we'll be able to see.
Okay. Yeah.
Now, do we expect that the depth of the ice is like the same everywhere, or do we expect variation? So in some areas it's a lot thinner, and therefore you could, probably have a much better chance of penetrating through that ice into the water.
Yeah, we will be looking for that. It probably shows at least some slight differences, but how much we don't know.
Right. Now, one of the things about Europa, and I think this was from the Voyager mission, is the linear, the cracks everywhere, and you can see it in the image the slide that you're showing. So, can you say a little more about those cracks? Like I mean, they seem unique in a sense, right, because of their length. But
Yeah.
how deep are they? And if you put the radar, along the crack, so you're getting a little bit of an advantage, not much, but a little bit to see maybe the ocean is closer. Like what caused those cracks? That's kind of what I'm getting at.
Okay, so these cracks, and I have this other picture here that shows some of these cracks. And one of the things to see here is that they all didn't happen at the same time. This crack here overlays this earlier crack, and this crack here overlays this one. So there have been episodes of activity, and we believe it's tidal heating. Just as the Earth and the Moon exert tides on each other, so Jupiter exerts a tidal force on Europa, and it also applies to the solid body. Tides are also occur on solid bodies. So it's the, when you have a tidal bulge, it keeps moving, it releases its energies, mechanical energy, which eventually ends up as heat energy. That heats the object, and this is what causes this liquid ocean and active geology. And by the way, that's one of the purposes of this mission. We're going to look for active geology, which has been putatively, not definitively, but it looks like it's been observed on, from the Earth-based telescopes, mainly Hubble Space Telescope.
Yeah.
So how big are these cracks? Oh, they're, I honestly don't know. People have measured them, but I don't have, maybe it's like 100 meters, it's less than a kilometer, 100 meters or so.
Okay.
But, and you can see, it looks like there's some kind of dust there, maybe some of that is material that actually comes from these cracks, but we can't see down into the ocean. Okay. In fact, remember on Enceladus, it also had kind of cracks too. We call them tiger stripes. They were not, that ocean is closer to the surface, and we weren't able to see any liquid water underneath. So we can't see to the ocean. This is only a small fraction of the distance to the ocean, these little, this crack that you see.
So I've got to ask a question. So they are looking for cryotectonics with the Europa
Absolutely,
Clipper?
yes, yes, definitely.
Cool.
When you mention about the tidal heating, I mean, the Jovian system is famous for Io, right? The most
Right.
volcanically active object in the
Yes.
solar system, and that's through the tidal effects.
Yeah.
Right. From Jupiter, and also these moons have what's known as resonances, where they make a even number of orbits for each other. So there's complex series of what are known as secular resonances, and they actually exert tides on each other. So, but it's I believe it's mainly from Jupiter that the tidal force would have to be, because its mass is so great.
Now it's interesting when you look at the ridges. Naively you would expect some ridge develops, it's like tidal forces, that would reoccur, like that would open and close and open and close. Yet in this case, you're seeing things almost perpendicular to some of the major ridges that you see here. So it's almost like cracking the surface of an egg in some sense, right?
Yeah.
So it's
Yeah.
really strange in that sense.
Yeah, there've been various theories for that. I mean, one of them is it's just chaotic. I mean, there's so many factors happening in there that whether it goes in this direction or that direction, it's just a matter of chance. But there's also this idea that maybe as we know, right now, Europa has the same face towards Jupiter, like most major moons in the solar system. But maybe in the past, wobbled more, or maybe it wasn't quite, or it turned around, or there's some, instability that occurred, so that its librations were even more extreme. There are theories like that, but the problem with a lot of those dynamical theories is that just because it could happen doesn't mean it did happen. It's kind of the hallmark of dynamical modeling. So that could be a factor, but it could be another factor, that maybe some important physical properties of Europa are changing. I mean, maybe there is a big impact. Now there are not that many impact craters on Europa. In fact, here's the biggest one down here in the corner, Quill.
Oh, right.
And that means that it has been active in the recent geologic past. Its age is somewhere between a couple 160 million years, a couple 100 million and 60 million years. So it's relatively recent. The solar system is 4.65 billion years. So that's recent in geologic time. But it doesn't have many craters. But suppose there was a big impact, it could have knocked it off its, facing of Jupiter and caused maybe some type of chaotic crack. We just don't know. I mean, we'll find out more.
I can think of, of a large impact, almost like the mascons on the moon, that can the Europa Clipper mission detect any type of gravitational anomalies where there seems...
Absolutely. That is one of the things the gravity experiment will be able to detect. Whether it's in equilibrium, the gravitational equilibrium, or whether it has, as you said, a mascon someplace near the surface. It may even be able to do things like characterize the core of Europa through the gravity experiment.
Cool.
Yeah, I mean, we've talked about a few months back, there was a group that released a paper about the same kind of situation, but with the Earth. Remember, there was an off-centered, a
Mhm.
large, massive object supposedly, which could be the result of some large, I don't know, we call it planetoid or something early on in the formation of the Earth. So, in some sense, that could be ubiquitous across the solar system. That this is just the natural, coming together of various massive objects early on in the solar system history.
Yeah. Well, the whole face of the moon is determined by this late period of bombardment, which actually has become controversial. Some scientists don't even believe it existed, but for sure, the face of the moon had massive melting due to giant asteroidal impacts, and that's what caused the oceans, the Maria on the moon, and also the mascons are probably their previous asteroids that crashed into the moon.
So, Bonnie, I'm going to ask a question and I don't know the answer to. I know there was a lot of talk, but I don't know. I haven't followed it to see if we came to a successful conclusion. But when you look at the near side of the moon, you see all the Maria and stuff, but on the far side, you don't see that as much. So, do we understand why that's the case?
We don't, it could be some kind of a gravitational, a tidal, a combination of gravitational, tidal kind of, going to the lowest energy state. It could just be more stable as it became tidally locked. But again, we don't really know the answer to that. Why, all these mascons are on the far side of the far side of the moon, and the mountainous terrain on the moon is also over there, but we don't quite understand that. So some kind of a gravitational, the moon did seek some kind of a gravitational equilibrium at that point, early in its formation. And I think you and most of your viewers know that the favored explanation for the formation of the moon is right now is that a Mars-shaped body crashed into the Earth and caused this debris disk, and all those fragments of that collision fairly rapidly coalesced to form the moon.
Yeah.
Right, and then there could be a leftover core of that Mars-shaped object that's still inside the Earth. That's what we're seeing in these studies.
Absolutely.
Yeah, very interesting.
Mm-hmm. So, yeah. um,
So when we look at the surface of Europa, what would be different there? Let's say, I mean, I'm thinking of Titan. That's another spot where we have evidence for hydrocarbons.
Yeah.
Mhm.
And do we expect a similar? I know Europa doesn't have an atmosphere like Titan does, but is there any kind of explanation of why that's the case? Is there any way that in the future maybe, or maybe it happened in the past, that Europa would be more closely related to Titan? I mean, Titan is further away. In some sense, any energy sources getting from the sun is greatly reduced compared to
Yeah.
what Europa would experience. But you kind of wonder, why do you have this oddball Titan, and yet you have, when you look at the Galilean moons, they're just so much different than Titan. It's kind of unusual when you think about it.
Yeah. Well, Titan is kind of a world unto itself. It is the only moon in the solar system that has an appreciable atmosphere. It's about at the surface, it has the surface pressure actually more than that of the Earth. I think it's about 1.5 times that of the Earth. And like the Earth, its atmosphere is mainly nitrogen, but instead of oxygen, it has methane. And why did it maintain this atmosphere? Well, there are different reasons. First of all, it probably had a lot more atmosphere to begin with because it's massive, it's planet size. And Europa is only about the size of the moon. So any atmosphere, and has a tenuous atmosphere, but any atmosphere that would form would fairly rapidly escape because it just doesn't have the gravity. The thing about Titan and the reason it can keep its atmosphere, there are actually 3 reasons, and I'll get to the most interesting one last. The first one is it's colder out there, okay? And okay, if there are any physics students listening to this, that atmospheric molecules have the velocities have what's known as a Boltzmann distribution, and depends on the temperature, and the more rapidly they move, the higher the temperature is, the more rapidly they move, so they can reach escape velocity and leave the planet or moon. Okay, that's the only part. I'll stop any technical discussions now, but I figure there are some physics students, and that's why we have escape of planetary atmospheres, because of Maxwell-Boltzmann statistics. Okay, so it's cold on Titan. And also it has a lot of gravity. So gravity and temperature, those are the two things that keep the atmosphere cold and big. But here's another interesting one, that maybe there's active volcanism on the surface. There may be
Oh.
active methane volcanoes. In fact, different people have done analyses, theoretical modelers have done, calculations that suggest that that has to happen. So there may be, we did not find any during our, how many flybys did we have? I think we,
Oh, Lord.
I forget, I was on. the mission,
Cassini
but,
did quite a few.
I think about as many as we have in Europa, numerous flybys of Titan. And we had thermal, there's plenty of methane, of course. We had thermal mappers, and we had an infrared spectrometer to look through the atmosphere, and we had a radar, a traditional radar, which, yes, by the way, was really dimmed the lights in the spacecraft. I mean, this radar we have reason is much more efficient. It takes about as much energy as, say, a light bulb or something, but it is at least double that on Cassini. I forget the exact numbers, but in any case, we did not see any active volcanism, and we looked pretty hard. I just hope somebody in the future, an undergraduate student maybe, would look more carefully through all our flybys and see if there's any evidence of any heating. But we at least glossed over that. We kind of, like skimmed the cream off and didn't find any. So, but that is the third very interesting thing that may cause the atmosphere, that it's actively being produced by active volcanism.
That would be interesting.
Now, one way I'm thinking of like the Magellan mapping the surface of Venus. You find all the, calderas or whatever from a huge number of volcanoes.
Mm-hmm.
Is that something that we could look for also on Titan? It'd be to see any evidence. Maybe it was really active in the past, not so active now, which means why you wouldn't have the thermal data.
Yeah, we did see a few things. The one of the problems with Titan and the Cassini mission was you can see through the surface to a certain extent, because there are these windows in methane where you can see through to but it's not as clear as you can see, like, this image in front of you. So that was a problem. And, there were a few things that we thought were volcanic. I mean, we even, Pluto, the New Horizons mission, this Mount Wright, I think, showed this, what looked like a volcanic feature, but we're not totally sure. I mean, we see these volcanoes on Mars, and we're pretty sure that those are volcanoes because they're, they're rocky. But on some of these icy bodies, we're not really sure what volcanoes look like. So we didn't see any things that were as obvious as volcanoes on Venus or other rocky objects. So cryovolcanism is it's a different beast. So we didn't see any absolutely, yes, this is a volcano. There were things that were hints of volcanoes. But on Europa, I don't think anyone is talking about volcanoes on Europa. There are plumes, there's cryovolcanism, but it's not the classic, shield or cone volcano that we see on the, by the way, I'm not a geologist, I'm an astronomer, so my apologies if I'm using this terminology wrong. But there aren't features, like if you look at these cracks here, that seems to be, some of them you can see little white centers where maybe fresh ice is coming out. Here you see what looks like debris coming from, maybe it's dust of some sort, or even organics coming from the cracks. But we don't, then we see this kind of slurry, there's this chaotic terrain. It looked like slurries out onto the surface, bright spots, and then of course there were the plumes on Enceladus, which were just geysers coming out of these cracks. So they're not volcanoes per se. When we say cryovolcanoes, it's not really the volcanoes we see on the Earth. We don't really know what we're looking for. But there aren't any, at least with the Galileo and Voyager images, we haven't seen any classic style, silicate, rocky type volcanoes on Europa.
Now, I know Triton, that was one of the surprise when, I guess, Voyager 2 flew by. Right. Triton was the geysers. And and you could easily see them in a sense because they, if you colored the surface differently, it was a darker color. So could that be responsible for what we're seeing here in this picture that you of Europa's surface, that there you know, in the
Well,
past?
they could be similar types of particles, but I don't think the mechanism is similar. I'll tell you why. If you look at those geysers on Triton, they're all in the polar cap. And there's an interesting phenomenon that has been studied on Mars. I think they're called spiders, where these plumes that come up when the polar cap recedes, you know, in the spring, you see similar, we've never actually seen the similar geysers, but we know they're there because they leave these deposits. So when these carbon dioxide, water and carbon dioxide polar cap of Mars heats up, these geysers come out and cause plumes, we think, and then the deposits. So it looks like there's a similar thing happening on Triton. It's not really cryovolcanism like that's coming from a subsurface ocean. It's related to the sublimation of the polar cap.
Okay.
Interesting.
Yeah, I hadn't heard that, so that's
It's actually the one of the main. Personally, I think it's the most convincing, and I know there are other theories that it comes from the subsurface, but then why only on the polar caps? And there was even Andy Ingersoll and I think Candy Hansen had a model that had there were actually dust devils on the surface. I think that's been largely not discredited, but disfavored. You know, so. We don't know really what it is. In my opinion, it really looks like it's related to the sublimation of the Martian polar cap. I'm sorry, of the Triton's polar caps.
okay.
Yeah, in some sense, I mean, you come up with ideas, hypotheses, but the real thing is what suite of instruments and what observations do we need to make to try to discriminate between these various ideas that people have?
Right.
Yeah, you know, it's kind of interesting that the payload on Europa Clipper is very similar to our last flagship mission to the outer solar system, which was Cassini to Saturn. We have the same types of spectrometer. We have cameras. We look across the electromagnetic spectrum to look for the composition. That's one of our goals. The camera studies the geology, the surface. Then the spectrometers, the infrared spectrometers, map the composition. And then we also have a thermal spectrometer that maps heat and the characteristics, the textural characteristics of the surface. And then finally, we have a UV spectrometer that studies the tenuous atmosphere and possibly the plumes, if there are any. So that's kind of the same type of remote sensing instruments we had on Cassini. We have a radar, but it's different, newer technology. And then in addition, we have all these what are known as in situ experiments. And we used to call them fields and particles experiments, which I like that term better because in situ to me means you're on the surface. You're actually looking I think it means in place in Latin. So, but now they're called in situ experiments. These are experiments that detect not only the magnetic field, but also the plasma, both the neutral and the charged particles. They kind of just sniff around the spacecraft and try to understand its environment and try to characterize any possible particles that would come out of any cryovolcanic events.
Now, you mentioned about possible organics on Europa. So if there is such a thing, then it sounds like what you're describing is that Europa Clipper will be able to say that, right, whether there's organics or not.
Yeah, that we will be able to. And the third, one of the three requirements for life is that there's food, that there are organic molecules there. And we were able to detect that. The spectrometer the infrared spectrometer was able to detect that on, for example, Iapetus, which is this weird moon of Saturn that's half dark and half bright. And in fact, there's a paper by Dale Cruikshank that actually says they're polycyclic aromatic hydrocarbons, which are these complex, really
That's
complex,
pretty complex molecules.
organic molecules. And you probably know that there have been organic molecules, including glycine, which is an amino acid that was detected on the comet 67P. And also, I believe there is some evidence that it's been detected in the interstellar medium. I haven't followed up what level of controversy that is. but it has been, at least putatively, this amino acid detected in the interstellar medium.
Yeah, I mean, the PAH is that's something you can get right from like exhaust from like a diesel vehicle or something, right? A truck.
Yeah, but,
You-
but that is ultimately organic, coming from, hydrocarbons, which were once living sources. But I believe you can, I mean, I'm not a chemist, but I believe you can create them, without light,
Yeah.
polycyclic. Yeah,
Right.
I mean, I guess, yeah, you can.
You-
Polycyclic.
Yeah,
aromatic.
they can. I think it takes the reducing atmosphere, reducing conditions, and some other, you know, energy source as we've discussed and things like that. And I was not aware that they possibly detected glycine in the interstellar media. I know they detected in the cold molecular clouds other organic molecules, but I didn't know glycine was there.
Yeah,
So-
well, the last time I checked, I haven't followed up on this, it was detected, but it was controversial. It wasn't confirmed.
Okay.
So, I haven't followed up on it to see if anybody else has detected, but it's definitely been detected in a comet and in, also some, meteorites.
I mean, you raise a good point too, because some of the things that you look for signs of life, quote unquote, can be, if you like, manufactured by non-living things. And here I'm thinking about the example of phosphine in the atmosphere of Venus.
Yep,
Absolutely.
that was really controversial.
Yeah. So it's very difficult to say 100% for certainty, okay, there's life there, this is the only way we can get what we're seeing, but that's not always true. You have to be very careful.
Yeah.
Yeah.
Even if we found some of our industrial waste gases in an atmosphere on an exo, you would have to step back and say, whoa, can we form this some other way? So, yeah, it's a testy scenario.
Yeah, that's like the technosignatures, right?
Right.
That we would look for.
There's the methane on Mars too, a similar controversy where, well, first of all, it's controversial how much, if any, has been detected, but you can be a byproduct of life, primitive methanogens, primitive bacteria that are living below the surface, or it could just come from some remnant volcanic activity or some kind of mineral process at the surface. And now scientists that work on exoplanets are working on how can you produce oxygen abiotically. There are ways, even if you detect oxygen in an exoplanetary atmosphere, there are ways that it can get there without life.
I mean, when you're proposing a mission and trying to sell it, I mean, it's taxpayers' money, you got all these interesting things that could possibly be, but really the selling point to me personally is you don't really know till you go there.
Right.
And if you never go there, then you'll never find out.
Yeah, that is so true. I mean, I look at the stuff that you pointed out the activity on Triton, totally, unexpected, but look at Pluto. I mean,
Yeah.
Lord.
did we think there was going to be, active geology, and active glaciers on Pluto? We didn't dream that, seeing that planet, I'm going to call it a planet, for the first time. It was really awesome we'd never expected that. So yeah, it's every time we look in a new place, it's so different.
And of course, hindsight's always 20/20, so maybe Alan Stern and the rest of the people who worked on New Horizon would have less of a barrier to get through to get their launch, their spacecraft off the ground if they would have had some inkling of what Pluto was really like.
Right.
Yeah,
But-
and now there's an object in the Kuiper belt called Eris that we think is similar to Pluto, that it seems to be covered in some kind of active, if you're bright, if you live in the north, that ice or snow becomes dirty very rapidly. That after a couple days, snow has an albedo reflectivity of about 70%, reflects about 70%, whereas fresh ice reflects all of the light. So there's this Kuiper belt object known as Eris. This was the thing that dethroned Pluto from its, was the final nail in the coffin. It's actually smaller than Pluto, but it's more massive. But in any case, it has a reflectivity of 100%. And the only way we know how to get that is active geology on the surface. So here's another object. And this seems to be bright all around. It could be, who knows what's out there? Massive glaciers, massive volcanoes. We just don't know. We have to look. It's hard to get there though.
Yeah, I mean, a big selling point, if I think back in like in 1980s or even in the 70s, that it's interesting to explore the outer solar system because that's still the leftover primordial, in some sense, material from the building blocks of our solar system. But now what we're realizing, if I take what you're saying and what we've seen up to this point, is even though they're really far away from the sun, there's still a lot of stuff that's going on that otherwise we'd never know it existed.
Yeah, yeah. The Kuiper Belt was just, it was in the 90s. It's only like 30 years old and we've even known about it. So, of course, exoplanets are the next, frontier. But, one of the interesting things is that a lot of these organic molecules that were existed on the early Earth that helped life arise here came from the outer solar system. It was too hot in the inner solar system to form these complex molecules. So we think that they were transported to the Earth with comets and asteroids, and that's still happening today. And we think that some at least of the water on the moon came from comets.
One of the things that I remember, this would be probably in the around 96, 97 time frame, is that we understood about planet migration that otherwise I've never heard that term prior to that time, right? Where some heavier elements are found in stars that hosted planets, when we start finding planets. And that tells us, I wonder really what happened in the very early solar system in terms of planet migration. What was the seeds or seeds that ultimately formed the Earth, and where did they come from? Some of them come from the outer solar system and moved inward?
Yeah, yeah, that's a whole new area of investigation. And I was saying before, in the dynamical field, just because something could have happened doesn't mean it did happen. And there's so many scenarios for this planetary migration that it's hard to determine a lot of it's chaotic. What
Yeah.
exactly did happen. But when we look at these odd things in solar systems outside our own, the type of placing of planets, it really does imply that planetary migration is common.
Yeah. The other thing I'm thinking about when you go back to Europa Clipper is because it's going to have a nominal mission, at least 4 years, if not more, hopefully more than that, obviously, that we'll be able to see any changes over time.
Yes, absolutely. Yeah, that's true. We have looked for changes using the Voyager images and the Galileo images and haven't found anything yet. Various, graduate students and undergraduates have looked at that, and we haven't found anything yet that does evoke a change. But that doesn't mean that it maybe could happen over 100 years or 200 years or millennia.
Yeah. Now, the other thing to kind of change gears a little bit, so I know you've also been participating scientist for the DART mission, which was in the news just not that long ago. And that's an exciting kind of thing because we always worry about what could happen to us. If you talk about, what are the things in nature that could kill us, if you want to put it bluntly. And one of the things, of course, is the impact of a giant asteroid that would wipe out all the people on the Earth type of thing, all life on Earth. So can you explain a little bit about the DART mission and what was that about?
Yeah. So, I already did refer to the fact that objects, comets and asteroids, are perturbed mainly by Jupiter and come into the inner solar system. And, why are we concerned about this? Well, it's kind of obvious, and that is that one of these objects might hit the Earth. In fact, we are pretty certain now that that's how the dinosaurs met their end, that about 65 million years ago, a giant object, possibly a comet, I think right now, I think asteroid is more favored, hit the Earth, landed in the Yucatan Peninsula. We've been able to look at kind of map out the crater and also see a lot of evidence for this impact, such as iridium. There's a layer of iridium, which is very uncommon in the Earth, but it's the stratum, the layer of geologic layer that corresponds to this time, 65 million years ago in the Earth's history. There is iridium, a lot of this iridium on that particular stratum. So it has affected the history. There was a Permian extinction where something like 95%, 90 or 95% of life was obliterated. So these extinctions happen, and we believe that one of the major causes is impacts of these near Earth objects. So NASA is doing three major things to try to come to terms with this. First of all, to discover them. This is where things like the NEO Surveyor, this is Near Earth Object, NEOs for short. There is an infrared camera that NASA's working on to put into orbit and try to find these objects. That's the first thing. The second, and the goal there is to find 90% of them that are 150 meters or larger. There's that goal. Then the next thing is to track them, to understand their orbits, to calculate whether or not they're going to enter or hit the Earth. There's nothing now that possibly will. And then to characterize them. But the last thing, which may be the most important, is mitigation. How are we going to deflect these things if we find one is on an impact to the Earth? And there's all the way from just some local disruption. I mean, most of them, of course, will hit the ocean, but they'll cause a tidal wave, all the way up to massive loss of life and Earth species. So there are different things that scientists are looking at, like nuclear bomb, which of course would be controversial. But the thing that the DART mission was supposed to test was if you go to the asteroid and just impact it with a classical cannonball, which is what the DART spacecraft did, how much will it perturb its orbit, and will that be enough to deflect it from a terrestrial path? And we decided to go to a double asteroid, binary asteroid. About 15% of NEOs are binary, and hit the little one, which is called Dimorphos. Didymos was the big one, and Dimorphos was the little one. Hit it, and then it would alter the orbit such that the main asteroid's period would change. And scientists did calculations and totally underestimated. I mean, it was changed by over 30 minutes when we thought it would be a few minutes. So it looks like that method is pretty good. The impact. There are other methods, nuclear. Then there's the tractor method, and but this was the impact. Trying to push this asteroid off of its path. So that was the main thing. It was to investigate quantitatively a mitigation strategy, impact mitigation strategy. And there's a spacecraft the European Space Agency is building called Hera that is going to go to Didymos and Dimorphos, the pair, and look at the effects of the impact. It's actually going to launch about the same time that Europa Clipper is going to be launched from Cape Canaveral also. And I believe it's a couple years later, it'll be at the asteroid to look at the quantitative effects of the impact.
Nice.
Very interesting.
I'm going to read a comment from our College of Arts and Sciences here that came through, and that is fascinating and so exciting to think about all the potential knowledge to be discovered. Thank you for sharing your perspective. We love to hear from experts and appreciate your time. So I wanted to pass that along.
Thank you. Good to hear.
I guess we can bring this to. I mean, we could talk a whole
we could talk a
podcast
lot.
on just the DART mission and its implications. You always wonder. And just briefly, I wanted to mention the fact is when we map out all of the, let's say, the orbits of anything above a certain size. I think you mentioned 150 meters. Those orbits can be perturbed. So it's like a continuous thing, right? You have to, every so often, you got to redo this, right? You can't just rest on your laurels, right?
Yep. We're constantly looking at them and have various, telescopes. The LSST, the Vera Rubin telescope, are going to be observing these things constantly, as well as the NEO Surveyor.
Yeah. So we can't, have to be on guard all the time, really, when you think about it.
Right.
Well, yeah, I'm thinking about the mitigation effort too, right? Most of this, it relies on the fact that we know something's inbound a long time from now. So then we have a chance to get there and do something about it.
Yeah, I mean, the real thing is if something comes up, has a highly inclined orbit, and we can only, it's off the the plane of the solar system, and we just see it at the poles. That's the real hazard, I think.
Yeah, definitely. Anyways, well, I think we'll wrap it up. So If any of you out there who are listening to this podcast are interested in STEM or STEAM or anything related to higher education, feel free to come to the University of North Dakota, either on campus or remotely, or any other institution for that matter. The thing is, always keep learning.
Always.
Always. Now, before we thank Bonnie for being with us today, I want to read an excerpt. This is from a book by David Brown, The Mission. It's about the Europa Clipper. So if you're interested in at least one person's perspective of the challenging effort that it takes to get a mission, from the ground up and get it actually ready to launch, that book may provide you with some insight of that. But the last paragraph in David Brown's book is very kind of a good summary for this podcast. So I'm just going to go ahead and read it. The bottom of the European Ocean would likely look nothing like the one on Earth. The fine sandy stuff forming dunes down and along our ocean floor was composed of bits of shell, sand, and sea creature. It's all weathering and decomposition down there. The seafloor of Europa would be rough, more Martian than not. There's no weathering, no ground-up pieces of stuff settling out. Unless there's life, then it's anybody's guess. So with that, Dr. Bonnie Buratti, thank you very much for joining us, and we really appreciate your time.
Thank you, ma'am.
Thank you.
Thank you.